In this example, we have the vertical position of a traveling wave described by the equation y equals 0.75 centimeters, cosine 6.28x minus 314t plus pi over 4. And then we have a few questions. Okay, let's jump right in. Is the wave moving left or right? Let's remember our general equation for the waves. Y of x and t equals 0.75, equals amplitude times cosine wave number k times x minus angular frequency omega t plus phase constant phi. Now right here I wrote plus, but it could also be a minus. I wrote minus, but it could also be a plus. Minus is for waves that are traveling right. Plus is for waves that are traveling left. So for part A, is the wave moving left or right? We have a minus, therefore it's traveling right. So it's traveling to the right because the wave equation has the form kx minus omega t. Had it been plus omega t, it would have been traveling to the left. Okay, part B, what's the amplitude of the wave? We can just do a straight up comparison. The amplitude A is 0.75 centimeters. You can write that in meters if you wish. If you prefer centimeters, that's okay too. Okay, part C. What are the wave number, angular frequency, and phase constant? Wave number is the bit that comes before x. So your wave number is 6.28. Now we do have units here. Because it's the wave number, and wave number is 2 pi over lambda. 2 pi is in radians. Lambda is in meters, so the units are radians per meter. There's your wave number. Your angular frequency is the bit that's before the t. That's 314. Because omega is 2 pi over the period, 2 pi is in radians, period is in seconds, so omega is radians per second. And your phase constant phi is the last bit. Phi is equal to pi over 4. You can write in radians. Also, it is just implied because you have a pi, so if you leave it out, that's okay too. Okay, there's A, B, and C. What about the wavelength and the period of the wave? I kind of gave a hint when we defined k and omega. K is 2 pi over lambda. That means lambda is 2 pi over k. 6.28, or let's just write 2 pi. 2.2 times pi divided by 6.28. 2 pi 6.28 over 6.28 radians over radians per meter gives us 1 meter. Okay, for omega, omega is 2 pi over t, which means t is 2 pi over omega. Omega is 614, or 314. That's in radians, radians per second, gives us t is equal to 0.0200 seconds. Okay, that's A, B, C, and D done. Ran out of space, so let's go on to a fresh sheet of paper for part E. Part E, what is the speed of the wave? So part E asks for wave speed v. So our wave speed v, you can calculate it in two ways. V is equal to f times lambda, and it's also omega over k. We know what our omega is. It's 314 radians per second divided by k, 6.28 radians per meter. Putting in my units here so you see where the units come from. Do that on the calculator, you should get 50 meters per second. So our wave speed is 50 meters per second. Had you done f times lambda, you would have got the same answer. Next question. Here's where we start to get a little bit more in detail. At the position x equals 0, for what time is the wave at a maximum? So For part F, we know that x equals 0, y is a maximum, that means it's equal to the amplitude, and we're trying to find the time t. Okay, so let's start with our equation for y. So y is the amplitude, 0.750 centimeters, equals 0.750 centimeters times the cosine of 6.28, that's times x, but x is 0, minus 314t plus pi over 4. If you were more of a symbols person, you could leave this in symbols for right now and then sub in your numbers later. It doesn't really matter. I'm going to divide both sides by 0.750. 1 equals cosine 6.28 times 0 is just 0, minus 314t plus pi over 4. Here's where you do have to be kind of careful with your numbers here. A couple of things to point out. First of all, 314 is radians per second. Pi over 4 is in radians. It means all of this stuff is in radians. So calculator in radians mode is first thing. Second thing, your t is buried inside the argument of a cosine. That means you have to get rid of the cosine before you can solve for t. You couldn't just divide both sides by 314 and subtract pi over 4 because it's all stuck inside the argument. To get rid of the cosine, you have to do the inverse cosine of both sides. So the inverse cosine of 1 is the inverse cosine of a cosine. That leaves us with just the argument. Okay, what's the inverse cosine of 1? When you do the inverse cosine of 1 on your calculator, you should get 0. So 0 is equal to minus 314 times t plus pi over 4. That means t is equal to minus pi over 4 divided by minus 314. So I took the pi over 4 to the other side, then I divided both sides by minus 314. Do that on the calculator. What we should get for our time is 0.0025 seconds. Okay, this of course is not the only time. It is the first time, but when are the other times? There's kind of a mathematical way and a more intuitive way. A mathematical way could be to go back and find the other values of inverse cosine of 1. It's not just 0, it's a whole bunch of angles. So that's one way to do it. But let's think about the graph and what the graph looks like. So our graph looks something like this. So this is time, this is y. This is our first time that we already found. This is t1, that's 0.0025 seconds. Our next time is going to be one period later. So there's our next time. There's t2. T2 is equal to t1 plus the period. Our third time is going to be another period later. So why don't we write down t2? So t2 is t1 plus the period. Because cosine is periodic, it repeats over and over. And when we're looking at the time dependence, it repeats with period. So t2 is t1 plus the period. Our period was 0.02 seconds. So t2 is 0.0225 seconds. t3, I'm not going to do too many of these because it's boring, is that time t2 plus period, add on another 0.02, and so on. So you can calculate a bunch of these, or you could write it in a more general format. All of the times at x equals 0, our string is at a maximum for any time that it's 0.0025 seconds plus some number times the period, where that number is 0, 1, 2, 3, 4, 5, and so on. That gives us all the values of time where our string is at the amplitude or the maximum height. Okay, the last part of this example, at time t equals 0, what positions give us maxima and minima? So this is where we hit pause on our simulation at t equals 0, and where are the high points and where are the low points? So it's going to be similar to this, but now we're asking what happens if t equals 0. Just make sure everything's on the screen there. Okay, so let's get started with the equation again. So part G, we know t equals 0, y is equal to plus a, and y equals minus a, and we'd like to know what are the values of x that give us those conditions. So let's start with the maxima. See where that takes us. So if y is equal to positive the amplitude, 0.750 centimeters equals 0.750 centimeters times cosine 6.28 radians per meter times x minus 314 times t, but t is 0, plus our phase constant of pi over 4. Divide both sides by 0.750. 1 is equal to the cosine of 6.28 times x plus pi over 4. Again, if I want to solve for x, I have to get rid of my cosine, so I'll take the inverse cosine of both sides. The inverse cosine of 1 is 0. Now I want to solve for x. Take my pi over 4 to the other side. That makes it negative. Then I have to divide both sides by 6.28. Radians over radians per meter gives me an answer in meters. But this answer, negative 0.125 meters. That's not really sensible because we're looking at values of x which are positive. So what are we going to do about that negative? So we want x greater than 0. Let's think about where we can go from here. Again, we can go back to what different values of inverse cosine of 1 is equal to, or we can look at our graph and see if that's helpful. So our graph of this function, 0.75 times cosine 6.28x plus pi over 4, looks something like this. So here's x, here's y, if you love your trig functions, you can probably go ahead and plot this just by looking at the equations. If you don't love them so much, you could go ahead and calculate a few values or pop it into Excel or what have you. Up to you, but it can be useful to have a graph. Okay, what number did we find? We found that y was equal to a when x was minus 1.125. That means we found a value back here. Okay, so it's not wrong to draw a graph back here. It wasn't what we wanted, but it wasn't a wrong thing to do. So when x was minus 0.125 meters, y was equal to the amplitude a. Okay, this part of the problem, we're trying to find the maxima. So when is the next time, or what is the next position where y is equal to a? That's over here. Y is equal to a again here. The distance between any two crests, that's the wavelength lambda. So this next distance, where we next have a maximum, that's x, or, sorry, I won't write an x, I'll say minus 0.125 plus lambda. So that'll give us my next position of x. So y equals a if x equals minus 0.125 meters plus lambda, lambda is equal to 1 meter, 0.750 meters. Okay, that's my first value of x, where y is equal to the amplitude. What about my next value? Well, my next value is over here. That's another wavelength longer. So this value of x is 0.75 plus lambda. can keep this up. Every time we go up, we increase x by one wavelength, we get a new amplitude. So we could write our general equation, y equals a for any value of x equal to 0.750 meters plus some multiple of the wavelength, where n equals 0, 1, 2, and so on. Okay, that's my maximums, or my maxima, sorry. What about my minima? We could go back to the drawing board. We could plug in minus 0.75 here, but maybe we don't have to do that. So if I look at my first minima, that happens right here on my graph. What is this value equal to? Well, if the distance between crest to crest is a wavelength, then the distance between crest and trough is a half of a wavelength. So this value of x, so this first minimum occurs for minus 0.125 plus lambda over 2. So that's going to be my first minimum. So y equals minus a if x1 equals minus 0.125 meters plus a half of a wavelength, 1 meter, divided by 2. So 0.125 plus 0.5 gives us 0. Hang on, let's just make sure that's correct. So 1/2 of a wavelength later, 0.5 minus 0.125. Yep, I knew I was doing something funny on my calculator there. I'm famous for it. 0.375 meters. Okay, my next minimum is another wavelength along. So over to here. Remember, the trough to trough distance is also a wavelength. So x2 is x1 plus lambda. 0.375 meters plus 1 meter equals 1.375 meters. And then my next minimum, I don't have it drawn here, but that would be another wavelength over. So my minima, y equals minus a, occur for x equals 0.375 meters plus n times lambda, where n equals 0, 1, 2, 3, 4, 5, and so on.